In this reaction, we'll be doing a coupling called a Wittig reaction. Right? And this is the first part of our lab where we're going to create a chemiluminescent molecule. Right? So in this part, we're going to create our fluorophore, that is the molecule that will generate the light. So Wittig reagents have a phosphorus with 4 bonds, so it's positively charged, attached to an sp3 hybridized carbon, right? These are called alkyl triphenylphosphonium intermediates, and usually they are halide salts, right? So you have 3 phenyl groups, sp2 hybridized carbons, and an sp3 hybridized carbons on that phosphorus, which gives it a formal positive charge. We make these with SN2 reactions, right? The triphenylphosphine, right? Its unshared pair acts as a nucleophile, attacks the sp3 hybridized carbon, right? Halide ion of an alkyl halide. Halide ion acts as leaving group. That creates, right, the phosphonium, which is the positive. The halide is the negative. Now, the Wittig reagent that we're going to use is a benzyl group, right? The benzyl group is our holds our sp3 hybridized carbon, right? Then we've got the triphenyl groups as the other 3 groups on the phosphorus. And we are going to use this pre-made. Right? We're not going to have to make it ourselves, right? This is how it was made, but we've got it as a pre-made compound. So after you've got your Wittig reagents, how does the reaction proceed? Well, that Wittig reagent needs to be deprotonated, right? And here they're showing a molecule of the solvent DMSO, right? I will admit I don't like that approach, right? So instead of DMSO, right? Oh, I want to erase all this. Right? Instead of DMSO, I would prefer that we show the hydroxide ion. We're going to do this in the presence of sodium hydroxide. So let's use the hydroxide ion as our base to deprotonate that sp3 hybridized carbon of our Wittig reagent, right? That would create water as the conjugate acid product. And this deprotonated product, because phosphorus is so much bigger than carbon, pi bond overlap is difficult. And so it tends to form this positive negative ion, right? And a species that is a positive and a negative, that is, it is something we call a Zwitter ion, where the formal charge is on adjacent atoms, right? That's what we call an ylid, right? An ylid. So we have created a phosphonium ylid. Now, the carbanion part of the phosphonium ylid can act as a nucleophile to attack the positive carbon of the carbonyl. But then the oxygen of the carbonyl can act as a nucleophile and attack the phosphorus, which makes these two new bonds. Let me actually highlight them. This creates a product called a cyclic oxyphosphatane. Right? And being a four-membered ring, it has a lot of ring strain. And it can undergo a spontaneous rearrangement where a pair of electrons falls there. This pair of electrons goes, actually, I don't like the way they drew that, goes here, right, to form a second bond between oxygen and phosphorus, right, here and here, right, which creates a new pi bond, making an alkene, right? And they were showing it leaving, right? But I think it's better to show it as a pi bond here, right? And we get our stable phosphorus product. A triphenyl phosphine oxide. Right? But whether you show it, again, as a zwitterion or as the neutral molecule, it is stable, right? And its stability drives the reaction forward. So here are some examples of using a Wittig, right? So here we have an aldehyde, benzaldehyde. We have a methyl triphenylphosphine. Here it's shown with a double bond, but I think it probably better to show that as a single bond, that as the negative, that as the positive. But, right, however we draw that CH2 group replaces the oxygen to form an alkene. Right? So here it is again on the bottom. Let me actually clear that up so that it doesn't look so much like a, right? So again, we would prefer to draw it in the ylid form, right? Single bond, unshared pair on the carbon, right? If we were drawing the, right, that would attack there. That would attack the phosphorus. Please draw them in a better orientation than that. But again, right, that group replaces the oxygen, right, to create an alkene there. But then you get, right, oh, I missed one carbon, right? There's your alkene, right? That's your new bond. And so if you're looking at reversible processes, if the Wittig is the forward way to go from a carbonyl compound to an alkene, then ozonolysis is a reverse process, going from an alkene back to a carbonyl compound. Right? So here's the reaction we're going to do. Our benzyl triphenylphosphonium chloride is our Wittig reagent. right? And this, right there is our sp3 hybridized carbon, right? We will use 9-anthraldehyde, right? The carboxaldehyde of anthracene as our carbonyl target, right? And so our product will be that benzyl group linked to the 9-anthraldehyde to create this long conjugated system, right? So this will be our fluorophore, right? Our molecule that will generate the light. And this will be that stable byproduct that, right, its stability pulls the reaction forward. Right? So here's our mechanism, and I thank Dr. Stickney for creating this layout to make it easier, right? So we're going to use sodium hydroxide as our base, as I said earlier. So it can come in and deprotonate the sp3 hybridized carbon, leaving that unshared pair of electrons and creating our ylid, right? Our positive and negative on adjacent atoms. Right? Then our carbon acting as nucleophile attacks the carbon of the carbonyl, but it has to give up electrons to do that. So simultaneously, the pi electrons act as nucleophile to attack the phosphorus, and that creates that new bond, and the nucleophilic attack of the carbon creates that new bond, right? And so this is our oxyphosphatane intermediate. That four-membered ring is unstable because of angle strain and torsional strain. And so then, right, the electrons can fall from here to make a pi bond. Electrons can fall from there to make a pi bond. That breaks the ring. It creates a pi bond there and a pi bond there. And we create our products. Okay, some technical notes that we get from Mr. Wyeth, right? First, we are working with strong solutions of sodium hydroxide, right? Strong solutions of sodium hydroxide can be very dangerous. Remember, sodium hydroxide, if you get it on your skin, it doesn't burn, so you don't know it, right? But what it does do is it converts the fats in the oil on your skin into soap. And so if your fingers suddenly feel slick, you may have gotten sodium hydroxide on them, right? So wash with lots of water. Okay? Now, right, you really should wear gloves, right? But if you notice that your fingers are feeling slick, you may have gotten sodium hydroxide on your fingers. Maybe someone dropped some on the bench. Maybe there was someone on the outside of a container, right? Make sure that you're using your gloves and you're aware. right? The sodium hydroxide should be made up as a 50% solution, right? So the specific gravity of a 50% solution is about 1.52 grams per milliliter. So since we're going to use a small amount, we can measure it in drops, right? Mr. Wyeth has previously measured that 20 drops of this solution is a milliliter, right? So we will lose less if we drop it out of a transfer pipette than if we try to measure it in a small graduated cylinder, right? So for this, use the transfer pipette. And this measurement, rather than trying to put it in a graduated cylinder, right? When we're done, we have to get this dry, right? We have to use our drying reagent, so we're going to use calcium chloride pellets to dry it, right? Just as a naming reminder, right? 2-propanol, right? A poorly designed common name is isopropanol. So look for either a bottle that says 2-propanol, isopropanol, or isopropyl alcohol. Those are all synonyms for the same compound, right? Now, after we are done, we're going to test our fluorescer by putting it in ethanol and shining a UV lamp on it. So you'll take a medium-sized graduated cylinder, about a 25 milliliter graduated cylinder, right? You will put some ethanol in it, and then you will drop a few crystals of your product. And you will watch those crystals fall through the ethanol as you use the UV lamp, right? It will fluoresce, right? If you have the right product, the product will fluoresce. That is, it will glow, right? Because it's converting invisible UV light into visible light. That's what fluorescence means, okay? So it will take invisible UV light, create visible light, and so it will appear to shine in the presence of this. Now, we will need this product for the following week, so save the product. Don't throw it away, right? We will be using small stir bars. Pay attention to them. Don't pour them out into the sink, right? Right? Pull them out with a magnet before pouring. Right? After you've dried it with calcium chloride, give that calcium chloride an extra rinse with a little bit of dichloromethane to improve your yield. Okay? Now, to keep the product until next week, methylene chloride tends to dissolve plastic whey boats, right? So either use glass, some kind of glass container, or use an aluminum whey boat for your storage. But remember to label it all properly. So that's your mechanism and your chemistry. Make sure you read the procedure carefully, right? Make sure you follow these extra notes.